A single machine can cost over 200 million US dollars. It weighs more than a tank. It contains over 100,000 components. It ships in dozens of containers. And without it, the world cannot produce the most advanced chips. This machine is EUV lithography. Today, only one company on Earth can manufacture it at scale. That company is ASML in the Netherlands. One machine, one supplier, one industrial bottleneck. Every modern chip must go through lithography. Phones, AI servers, data centers, cars, weapon systems, and satellites all depended on it. No lithography means no advanced chips, and no advanced chips means no modern digital economy. Lithography defines how small transistors can be printed, and transistor size defines computing power. This is the foundation of the entire semiconductor industry. The extreme ultraviolet lithography, known as EUV, is required for 7 nanometers, 5 nanometer, 3 nanometer, and smaller precise nodes. Without EUV, advanced chip cannot be mass-produced efficiently. ASML is the only one supplier, not the best supplier, the only supplier. Each EUV machine costs roughly 200 to 350 million US dollar. Each machine weighs about 180 tons. Each machine contains more than 100,000 parts. Each machine relies on more than 5,000 suppliers. The assembly time for one machine is about 12 to 18 months. One machine equals the complexity of the entire factory. The EUV requires synchronizing multiple extreme technologies. These include ultra-high vacuum systems. They also include plasma light sources. They require precision mirrors. They require nanometer level vibration control. They require advanced optics. They also require high-speed computation. The mirror system alone is produced by ZAS in Germany. The surface precision requirement is extreme. The error must be less than 0.1 nanometer. This is smoother than almost any surface ever manufactured at industrial scale. Each mirror costs millions of dollars. Each machine uses dozens of these mirrors. This supply chain took decades to build up. ASML began EUV research in the 1980s. The first prototypes appeared in the 1990s. Commercial viability arrived around 2018. Mass adoption begins in the 2020s. The total development timeline exceeds 40 years. The research and development investment reached tens of billions of dollars. This is not a product cycle. It is a generational cycle. Even if a country starts today, it may take decades to reach the same reliability level. Without EUV, chip production stays at 28 nanometers or above. Alternatively, manufacturers must rely on multiple patterning processes. Multiple patterning is slower, it's also more expensive. With EUV, there are fewer processing steps. The yield becomes higher, power consumption becomes lower, performance becomes higher. A modern AI chip may require hundreds of billions of transistors. Without EUV, producing them efficiently is nearly impossible. One machines equal one ecosystem. That is a reality in the real world. Each advanced semiconductor fabrication plant may require 10 to 20 EUV machines. The total investment per fabrication plant may reach $15 to $25 billion or more. TSMC depends on ASML deliveries. Samsung depends on ASML deliveries. Intel also depends on ASML deliveries. Even these companies cannot build EUV machines themselves. This means the entire global chip industry depends on a single supply chain alone. Lithography determines AI development speed. It determines military electronics. It determines data center capability. It determines consumer electronics. It determines future computing power. Now, whoever controls advanced lithography influences the ceiling of the digital world. This is not just a manufacturing issue, it is a structural dependency. Advanced chips power artificial intelligence. Advanced chips power defense systems. Advanced chips power finance systems. Advanced chips power communication networks. Advanced chips power cloud infrastructure. Advanced chips require EUV as well. So the question is this: how many countries truly control the foundation of computing? The answer is smaller than most people think. Lithography machines are rarely seen by the public. They sat inside a clean room, far away from attention, but they quietly define the limits of modern technology, not through headlines, not through speeches, but through physics.